Okay. Yeah. So last time we had left off. Can you guys hear me?
Yes.
Okay. Yeah. Actually, I seem to have some. My internet is really poor right now. So let me know if my audio is breaking off. Okay.
Yeah.
Uh,
So
so
far, it's good.
okay, cool. Yeah, I'm actually at my parents' place now. So yeah, the internet is here is really bad. Uh, so last time we had left off till here, and where I think we were using LSTMs with 2 layers, and yeah, so now we'll improve this by using regularization. So what we had noticed was, even though we were getting good accuracy, we can see that there is a bit of overfitting towards the end, which is a sign that regularization would help. So, um, so one technique of doing regularization is data augmentation, which is quite difficult for text, but it is quite often used for images. Uh, so one technique of, because usually in text, data augmentation is quite computationally intensive. Like one example would be to translate it into another language and then back to the original language, which is obviously quite expensive. And data augmentation for text is not a well explored space. And other techniques of, so we'll go to other regularization techniques. And few of them were introduced in this paper, which is regularizing and optimizing LSTM language models by Stephen Merity and others. So they introduced, I mean, they didn't introduce, but Dropout existed previously, but they showed how effective use of Dropout and these two regularization techniques, that's activation regularization and temporal activation regularization, could allow an LSTM to beat state-of-the-art results, which required much more complicated models. So an LSTM with these three regularization techniques is called an AWD LSTM. So this is the architecture introduced by these people in this paper. And we look at all of them. So Dropout, I think we are quite familiar with it from previous architectures. It's basically uh, just dropping out some nodes in a layer randomly with a given probability. So suppose you have a dropout of p-value equal to 0.5. So each node would be dropped with a probability of 0.5. So at the end, you can expect half of your nodes to be just zeroed out. So that's what dropout is. It helps in regularizing your network because you are training, you're ultimately training with a smaller network than previously. And like the other advantages are like it helps the neurons to cooperate better together. It makes the activations more noisy. Like when you randomly switch off different nodes, your activations become noisy, which makes the model more robust. And like another advantage is that it ensures that uh, this layer, if you can see, it ensures that the the next layer does not depend on few particular features to learn it. Since we randomly zero out different nodes, it ensures that all features are used in your network, and it does not just heavily emphasize on like a couple or like one or two features. What that results in is that the weights are evenly spread out for all the nodes. It does not get concentrated for one or two features. And when weights are evenly spread out, what happens is the like your like sum of squares of weights would be lesser. So it is kind of you are actually kind of implementing L2 regularization of weights, if you remember that, which is weight decay. So it also does that. So dropout is a convoluted way of implementing L2 regularization as well. It's just slightly different, but the concept is kind of the same. Yeah, so that's how dropout works. And so another thing that we do is when you randomly zero out a bunch of nodes, what happens is the sum of your activations in that layer gets reduced, and we don't want that to happen because like during testing time we don't do dropout, so we don't want the sum there would be higher, so your activations in the next layer would get messed up. So we want the expected sum of activations in the layer to be the same even when there is dropout. So what we do is we just divide the remaining nodes by 1 minus p, so that the expected sum of the activations is the same. We are just rescaling the node values. So in this, if you can see, there are 5 nodes, and we zero out 2 of them, and then the remaining node values are divided by 1 minus p, so that the expected sum of these activations remains the same. Yeah. Please ask if you have any questions. So like I said, at training time you do the dropout, but at test you don't do the dropout. All the nodes are always present, and this is how you would implement dropout in PyTorch. So dropout is a layer. That's how it's implemented in PyTorch. So the only thing that you need to pass when initializing it is p, which is the probability with which you drop out each node. And so like I said, we only drop out during training. So if it is in training mode, if it is not in training, you just return the same tensor. If it's in training, you make a mask. A mask is just a tensor of ones and zeros, and you use the Bernoulli distribution. So Bernoulli distribution is just it's just 1 or 0, and the with a given probability. So you can give a probability, say 0.5 or something, and then you can generate ones or zeros using the Bernoulli distribution. And then you multiply your tensor with the mask, so that some of them get zeroed out and some of them remain. So when it's multiplied by 1, it remains, and when you multiply by 0, it gets zeroed out. And then you divide by 1 minus p, so that the expected sum does not change, expected sum of activations. So there is a small mistake in this. It should be self.p, not p, because p is an attribute of the object. Yeah. And I did the same thing over here. I'll just show that. Okay. Yeah. So the only difference is that you have to write self.p, and you can make a dropout layer by just passing in the p value, and then you can just pass a tensor, and this is what your drop tensor would look like. So as you can see, some of them have been zeroed out, and the others have been multiplied by 1 and then divided by 1 minus p, so that the expected sum is always the same. So this is how you write dropout, but we have an n dot dropout, so you don't have to manually write this. Yeah. So PyTorch has so a PyTorch module has a dot train method. So when you call the dot train method, it sets the training attribute to true. And when you call the dot eval method of the PyTorch module, it sets it to false. Not just that module, every module it recursively contains, for all of those modules, the dot training attribute, which is this thing, is set to true or false accordingly. So that is how Dropout knows whether to actually do the dropout or not. Yeah, now we come to regularization. So these are the two regularization techniques. One is activation regularization, the other is temporal activation regularization. The activation regularization is quite similar to weight decay. In weight decay, we add a small penalty which makes the weights as small as possible. So basically, you add the, if I'm right, you add the sum of squares of the weights multiplied by a hyperparameter which is WD. So when you add it to the loss, what happens is it restricts the weights from getting too large. So here we do something similar, except that it's done to the activations. So to the loss, we add a hyperparameter which is alpha multiplied by the activations raised to the power 2 and the mean of all of those activations. So that is how you regularize the final activations. Yeah. And so temporal activation is something similar. So it's linked to the fact that we are predicting tokens in a sentence. Uh, so so the logic that they use here is that, so when you are, so in this example, your data looks like this. It's basically the words of numbers. So it's 1 2 3 4 5. So you're using 1 to predict 2, and you're using 1 and 2 to predict 3, and you're using 1 2 3 to predict the token 4. So so what the logic they're saying is that, let me just read this. That would probably make it clear. We are predicting tokens in a sentence. That means it's likely that the outputs of our LSTMs should somewhat make sense when we read them in order. So since we are just predicting consecutive tokens, their outputs, the consecutive outputs should also make sense. The consecutive activation should make sense when we read them in order. So temporal activation regularization is there to encourage that behavior by adding a penalty to the loss to make the difference between consecutive activations as small as possible. So the activations that we get after the LSTM layer should be as close as possible. So that's what temporal activation regularization aims to achieve. Mm. To me, it does not make too much sense. Like, so, like, like it says that the activations of consecutive words should be same, but so what they're trying to imply is that, but then the consecutive tokens can be completely different. Like they need not, suppose you are trying to predict some kind of like normal English text. So consecutive words might be totally different in their meaning. So that could cause the final activations to also be completely different. So so this does not make total intuitive sense to me, but it does seem to work. So yeah, and the way we do this is, so yeah, I can draw a picture for this. Just a minute. So your activations tensor is of the shape, batch size, sequence length, and n underscore hidden. So it looks something like this. So this would be, so this would be your batch size, and this would be your sequence length. And then you have, and then this, since this is the activation that you get from the LSTM, it is of size n hidden. So so this is a 3D tensor. So I can draw it like this probably. And let me just draw one more. Yeah, okay. And this, okay. And this dimension is n hidden. Yeah. So this is what each batch of activations looks like. You basically have a 3D tensor of size, batch size, sequence length, and n underscore HID dimensions. So so and then what they're trying to say is that consecutive activations uh, should the value of consecutive activations should be as close as possible, because that is the loss that uh, we are adding to the, when that is what we are adding to the loss. So the sequence length is along this axis, the SL axis. So here it is the value 16. So uh, so so basically using 1 we are predicting 2, and using 1 2 we are predicting 3, and using 1 2 3 we are predicting 4. And for all of these predictions we have the activation. So that is what is along this SL axis. So you can imagine like along this axis you have 16 activations. Like you can imagine like something like this whole square that you can see. So the difference in so this square matrix and this square matrix should be as close as possible. The difference between the values of each consecutive square matrices that you can see should be as close as possible, because they are actually consecutive tokens. So that implies their activation should also be as close as possible. So that is basically the concept behind temporal activation. I hope that made sense. So what they are doing, so how in this formula is, so the second dimension is the sequence length. So that is what we have to index, and we want to find the difference between consecutive activations. So what they have done here is they have started from 1. They have ignored the first activation and they have started from the second activation, because as we know it starts from 0, the indexing starts from 0. So we have gone from activation 1 to the end, and here they have gone from 0 to 1 just before the end. So they have, and -1 implies the last activation. So we have started from 0 to just 1 before the end. So when you subtract these, what happens is you are finding the difference between uh, consecutive activations, because this starts from 1 and goes till the end. This starts from 0 and goes till 1 just before the end. And then when you subtract them, you're basically finding difference between these consecutive squares that you can see, square matrices. And then you just take a square of all of those values and you take a mean. So you end up with just one scalar value for each batch, and then you just add that scalar to your loss. So that's how temporal activation is done. Yeah, so we basically need 3 outputs to be able to do all of this. One is the actual output from the model, that is LSTM output, then dropout, and then the last linear layer. So that is the last output. And then you need activations of the LSTM pre-dropout and the activations of the LSTM post-dropout. So the reason for this is that activation regularization is applied on the dropped out activations because we don't want to penalize the activations that become 0 afterward. So if they are ultimately becoming 0, there is no point in adding them to the activation regularization penalty. Whereas the temporal activation regularization is applied on the non-dropped out activations uh, because these zeros will create big differences between the consecutive activations. So we don't want that to happen. And in PyTorch, there is a callback called, in FastAI, there's a callback called RNN regularizer, which will apply this regularization for us. And there is one more trick they use in AWD LSTM, which is called weight tying. So what it does is, so in this sentence should probably make it clear. In a language model, the input embeddings represent a mapping from English words to activations, and the output hidden layer represents a mapping from activations to English words. So the mapping is trying to do the same thing. So intuitively, we expect that these mappings to be the same. So I can show this in a diagram again. So let me just think about this. Yeah. So you have an embedding matrix in the in your input layer. So that's of size. Hmm, okay. Yeah. So you have your embedding matrix, which is of size, vocab size, and n hidden. So each word is converted to an embedding, and your input to this is, suppose, let's assume that you are having a batch size of 1. So your input is just a single one hot encoding. It looks something like okay. So it looks something like this. So, and then you multiply it with this thing, and then you basically just indexes the row. So suppose your word is the first, like the first word in your vocab. When you multiply this one hot encoding with this embedding matrix, you just index out the first row in the embedding matrix. So that's what multiplying by one hot encoding does. And so this is the mapping that they talked about. It is basically the embedding matrix, and then what you get out is what do you get out? So you get something of you get a single vector which is of size n hidden. So here it was a size vocab size, and out what you get outside is is basically activations of size n hidden. So it's just a bunch of activations, or you could think of it as the embedding itself, just a bunch of activations, and then you pass it through the LSTM that we have. And after that, so what you get out of the LSTM is again the same thing. You get a bunch of activations. Okay. Okay. So after the LSTM, you again get a bunch of activations, and then you need to multiply by something. Let's call it some matrix X, and then what you want outside is a one hot encoding of vocab size. So basically, it looks quite similar to the input that we had. This is what you want at the end. So so as you can see that it's kind of symmetric. You have a mapping that goes from a one hot encoding of vocab size to an activation of size n hidden, and at the end you want an activation of size n hidden, and then you want to map it to uh, something in your vocabulary. So that's why this makes sense. Just a minute. So that's why this weight tying is done. So this matrix is made equal to this matrix. So that's what weight tying is. And yeah, so we do that by just initializing it in this way. Self dot h underscore o weight equal to I underscore h weight. So this is the embedding matrix weight. This is the matrix at the end. And so the rest of the architecture is similar to what we had seen earlier. So we have the RNN, which gives out the output, and then we do a dropout on that, and then we just pass it through the last output layer and return it. And along with that, we return the LSTM activation without dropout and with dropout, since we need those for the regularization stuff. And it's quite easy to do this in FastAI. You just have to write CBS callbacks. This is for resetting the model. And then it has the RNN regularizer. And then you just give it the parameters alpha equal to 2 and beta equal to 1. So I did this in PyTorch, which is a bit more complicated. So this part is the same. Yeah, this is again something similar to what we had seen last time. So the difference comes in the fitting and the evaluation part. So in fitting, so the model gives out 3 outputs and you have to store all of them. The prediction, the actual output, and then the LSTM activations without dropout and with dropout. And then the usual loss function, which is cross entropy, and we have to add the regularization stuff to that loss. So in FastAI, it's done automatically with the callbacks, but here we have to do it manually. So what I've done is alpha is an input argument to this fit method. I've taken alpha and I've multiplied it with the out. Out is the, so this is the activation regularization step. So out is the LSTM activations after dropout. I raise it to power 2. I'm squaring it and then taking the mean of that, multiplying it with alpha and then adding it to the loss.
Hey Gautam, question.
Yeah. Yeah.
Shouldn't you be actually doing it to the activations and not to the loss as you explained before? Because he's not doing it to the loss.
But you add it to the loss, right?
No, in this case, he is doing it to the activations itself, right? So you would have to use a hook to get your last activations and then do it on that. That's what the callbacks would be doing. I haven't looked into it, but that's my guess that the callbacks would actually be hooking into the last layer of activations,
mhm.
the callbacks in FastAI. So you
Yeah.
would
So
also have to hook using the PyTorch callbacks into the last activation and then doing the regularization, because it's not
right.
loss regularization, right? Just like you went through on the
So I didn't get the last
when
part. It is
explained.
not what regularization?
The TA or regularization is on the activations, right? Not on the
Yeah.
loss. Or am I missing something?
So I mean, you achieve regularization by adding the squares of whatever you want, either weights or activations to the loss. So only then you restrict the activations or the weights, right? Does that make sense? You here you want to control or restrict the activations from getting big. So out is my activations, is my activation from the LSTM after dropout, and I want to make sure that out does not get too big. So I am just adding mean of the squares of my activations to the loss. So
Yeah,
once I
he adds
add,
it to the loss too. You're right. Okay, you're right. He adds it. I thought he was just doing it to the activation, but themselves, but he's actually doing it to the loss.
okay, okay,
Yeah, you're right. It is to the loss. Okay.
yeah, thanks. And then you do it, and then you do the temporal activation part. So raw is the activation from the LSTM pre dropout, and as I've explained before, this is to just take so what this part will give you is consecutive differences of activations, and then you take a square of all of them and just take a mean. So you ultimately end up with a scalar value, which you multiply it with beta and you add it to the loss. Yeah, that's pretty much it. I don't think there's anything else. So yeah, so one more thing, you have to explicitly say that I'm training my model, and you do that by model.train, so that the when you actually do the forward propagation, the dropout happens, and when you evaluate, you have to say model.eval, so that the dropout does not happen. Dropout is not done. Yeah, and then you can fit with all of these stuff, and you pass in the alpha and beta value, and you get something like 86, which is same as what Jeremy got, I think. But and Jeremy uses a weight decay of 0.1. I tried the same thing, but it gave me horrible results for some reason. Uh,
Yeah, I think the
okay.
reason it gives you bad results is, in
Yeah.
fact, he explains, I think, in whatever prior, not this section, but the previous one, that either the first or the second part, that, or even maybe earlier, that um, Adam, when originally implemented, was doing something like this, right? Meaning adding to the loss and then also doing weight decay, which is not correct because
Okay.
you've already done uh,
Right.
the fixing, so you don't do further weight decay, um, and that's taking you away from L2, what actually L2 regularization does, because you've already implemented the impact on loss.
So Adam does L2 regularization by itself. Is that what?
Well, no, the original Adam implementation that they
Okay.
were using had an issue, and it was doing both, which was the reason that
Hmm.
Adam was not used and stochastic gradient descent was preferred, because of precisely this problem that Adam was using both. Like when you use weight decay and this, then you're using both, right? Meaning like
Mm-hmm.
you're doing weight decay and you're also um, adding a difference to the loss.
Right. Yeah.
And therefore, that was worse. And by removing weight decay or just keeping weight decay and removing the addition to the loss, so you do one or the other, but not both, is
Mm-hmm.
the point.
Got it. Got it. Yeah. And then there's one more thing that I tried, which is gradient clipping, which I saw was done in a few other examples, but that did not give me better results. But I didn't try much either. Yeah. So it gives quite good results, even when you do it in PyTorch. Uh, and then all of this callback stuff is done for you automatically if you just use a text learner, which is a subclass of learner, so you don't have to explicitly write callbacks again. And uh, I think the original AWD LSTM uses dropout in a few more places, like embedding dropout, so just after the embedding layer. And okay, I don't know the difference between these two, weight dropout and hidden dropout, applied to the hidden state between two layers. So you can do dropout after the other layers as well to add more regularization. And yeah, yeah, that's it for this notebook. I did not go through any of the questions, but if you have any questions, we can discuss now.
I was just going to talk about the dropout. Well, the various forms of dropout and regularization. Do you just generally make sure that every layer is going to have something? Um, because it seems like there's, I'm not sure if there's some, structured way to apply this.
So is your question that do we use dropout after every layer?
Yeah, I mean, it seems like a lot of forms of regularization. I'm not sure when to apply which ones, how many of them. It just feels a bit like, and also, well, yeah, I guess that's the first question. The second question, I haven't, I have to say the activation regularization is new to me. Up until now, I've only ever seen things applied to the weights. So I don't know how common that is. So I'm not sure if anyone's seen that anywhere else.
Yeah, it's new to me as well. I mean, I think this paper might have been the first one to introduce activation regularization. I'm not sure about that. I mean, as for dropout, uh, yeah, I guess you just, I mean, try it out everywhere. I mean, I'm not sure what would be the best way to see if overfitting is happening at each layer. There might be some way to check that.
Mm.
But yeah, I'm not sure. You just
I,
have to try out at dropout at each layer, and yeah.
I think this particular AWD LSTM, I mean, it's also three levels of LSTM, one on top of the other. It's not just the 16 sequence, but it's also 3 levels of LSTM, each feeding each other. So the number of parameters that this AWD LSTM has is just ginormous. Now, of course, you could also say that the same is the case with transformers. So whenever you have a situation where I think you have a very large number of parameters, it would be a good hint that you would probably, and again, all these are subject to actual empirical verification, as Gautam has done here, of saying, hey, I tried this, but it didn't give me better results. So that's the ultimate test, is trying it out. But whenever you have, the rule of thumb, I would say, is whenever you have a tremendous number of parameters and you think that you don't need as many of those to fit the model, and you might be better off using Dropout. And this particular model uses so many dropouts in so many locations that's why even in Yami's final implementation, he just abstracts all of them and says, here is a single value that you can twiddle with that then changes all of the remaining dropout, the other 4 that I mentioned here, and finds the right values for them. So I've found, at least in a lot of utilization, that this is almost an extreme case. I haven't found in any other instance where as much of dropout is used as in this particular case. But the general principle being, if you have very large number of parameters, then you're better off trying to regularize, because the chances of your overfitting and basically the chances of your network just memorizing the states that it sees are very high when you have that many parameters.
Right. Okay. So you need to have a relatively, well, just some idea as to how much parameters you're talking about, how much data you've got, and be able to do a rule of thumb calculation. Kind of. Okay.
Okay. I have a probably a really basic question, but why exactly does large activations imply overfitting? Like, why can't you overfit by having really small activations? Like, what is it about large activations that says that you're overfitting? Can you answer that?
Yeah, I think the best answer that I would refer you to, the best fundamental answer that I would refer you to is in this book called Introduction to Statistical Learning with R.
Yeah.
It of course uses R, but it's a very well written textbook by a couple of Stanford
I do
profs.
have that book. Yeah.
Right. So if you look at the regularization part of that book, it explains very well the answer. I think that's the best answer I've seen, or the best explained. I'll try, but I'm not sure I'll do as good a job. But the bottom line is that it prevents any particular activation from having overly influencing your output, which is just a different way of saying you have overfit, because basically that particular, and in fact, the dropout does the same thing too, conceptually, if you think about it. It just says,
Yeah.
I'm not going to allow any one node to have a disproportionate, quote unquote, I'm using all these non-mathematical terms, but
Right.
here the answer is more intuitive than mathematical. But the point being that you don't allow any particular weight or set of weights to have a disproportionate influence on the output. So by not allowing any weight to grow significantly bigger, if any, actually, I changed the language, any activation to be very large, you prevent that from happening, and therefore help the networks generalize and do a better job of generalizing to unseen inputs.
The best example that I've seen of that is if you try to if you try to fit a function that looks excuse me, that looks, maybe it looks quadratic, but then you try to fit it even better by using a cubic model, what you find is that it will start fitting to the noise, and the parameters that it finds, for a cubic model there are 4 parameters: the linear, the linear, the constant, the quadratic, and cubic. Those 4 parameters will tend to be very large when it tries to fit the noise. And then you'll see clearly that any data that would be outside of the data that you had wouldn't fit well. In other words, the cubic would start going crazy as soon as it gets close to the edge, close to the edge of your data. I don't know if you've seen an example like that, but that's what happens when you allow the model to go crazy and use whatever values it wants. It will fit. It will get a better looking fit, but it's actually fitting the noise.
Okay. Yeah. As a continuation to this question, like even weight regularization, I have some problem understanding it quite well. Maybe I can draw a diagram for that. And if I'm taking up your time, I mean, you guys can leave. So my question, it's like this. So weight regularization basically controls your weight from getting too big, right? So let's assume, let me just think about it for a second. Yeah, so let's assume that there is a model like this, something like this. So the true model, the actual model that you're trying to predict is y is equal to say 7x plus say 2 or something like that. And now you are having some sample data points that look something like this. And now your linear model that you predict would be something like this. So let me just finish up my question. So so the model that you get by your sample at hand would be something like it has a smaller slope, right?
Yeah.
So 4x plus whatever c or something. So my question is, when you so actually your true model has a higher weight. It has a higher weight than what I have. So regularization will make it worse. It would never make it better. So why does regularization always try to control your weight? Sometimes the actual scenario might be that you need a higher weight than what you have. So yeah, that's my question. Did that make sense?
Yeah. So yeah, regularization will. Well, regularization makes things worse. You're saying it makes the fit worse. Is that what you're saying?
Yeah, I mean, it would never make it better than what I already
That's
have.
right. That's right. But
Because
what it will do, it will allow you to generalize better in a new situation. It's basically showing you that you can't really fit things as well as you want to by not using regularization. You'll get a better fit to this instance of the data, but what you're actually doing is you're fitting the particular noise that's in this data set. And if you tried it on a new data set, you wouldn't get such a great fit. So regularization is screwing up your ability to fit so that you're not fitting so particularly to the noise.
But what if my true model needs higher weight?
Yeah, specifically, Gautam, I think the issue is that if you're underfitting, regularization will not help.
No,
So
but I'm fit. I'm having a reasonably good fit given the sample of data that I have. But for the population model, my weight is actually higher. It's 7x.
yeah, no, but what I'm saying is, so as Joseph was just saying, the point is that if you, and again, we have to think of when we use regularization is primarily, at least in the concept of neural network models, which have a tremendous number of parameters. So in the case of simple equations like this, most of those parameters would be zero anyways. There are just a few parameters that matter. And in such instances, those parameters might, and parameters, I mean the weights, those parameters might need to be whatever value they need to have. So, so you wouldn't regularize, I guess, what I'm trying to say to simplify is you wouldn't regularize if you are underfitting, which means that you're not even doing a good job of fitting to the data that you have, which is why you would allow the weights to grow, quote unquote, to get closer to the data you have by going from y equal to 4x plus c to y equal to 7x plus 2. Now, if on the other hand, right, so the cases when you apply regularization is when you have so many parameters and you're not underfit, but you're actually overfitting to where you have your network is, Joseph is explaining, is fit not just to the underlying data, but to the underlying data plus the underlying noise. So when you try to generalize, then you are failing. And that happens when you have a large number of parameters and your network has put overfit. It does not happen in the case where you're that in the example that you just cited. So in that case, if you are using regularization, it's not a given that you would benefit by that. Because it's a case where your data, quote unquote, has underfit in the example that you just gave of 4x plus c to 7x plus 2.
Okay. Yeah. So basically, you do regularization when you see that it's overfitting. That's what you're
Yeah,
saying.
and in neural networks, the reason it is more generally applied in most cases is you have large number of layers, and like we discussed with AWT-LSTM, it's like already you have a sequence length of 16, so n hidden is 16. The embeddings could be whatever, and then you have the LSTM, which is 3 deep. So by the time you do all that, you end up with millions of parameters, and then you run the very high risk of it just memorizing, because it can just say, oh, I'll just allocate a parameter to each of these things that I'm supposed to learn, and then I'll just remember that. And that does not lead.
Can you just repeat that last statement?
I'm saying the number of parameters that you have in very deep networks is
Right.
extremely large, right? For example, in some of these transformers and other things, I mean, the number of parameters goes to billions, hundreds of billions, in fact, I think. And that means that sometimes when you're training, the network can just, it has such large number of parameters, and all, if you think about it, in the neural networks, all they're doing is learning to adjust the weights and the parameters so that through this stochastic gradient approach, or whatever gradient descent approach you use, to fit those or twiddle those so that you can do a good job of predicting. But the twiddling can just result in allocation by the net, or quote unquote what they call sometimes as memorization by the network of the examples it has seen. So if you have a million parameters and you need to learn a much smaller number, it can just, the network can just allocate one parameter to each of the things it needs to learn, and that it has seen from the data that you're providing. So it's not quote unquote learning the essence of the data, it's just memorizing what the data is saying and allocating numbers to the parameters so that it gets the best result. That's another way of, and in the simpler example, it's just what Joseph explained with, like, as you go from a third level equation to a fourth level equation and so on and so forth, is you are fitting the noise. So you're beginning to memorize not just the essence, the parameters are beginning to reflect not just the essence of the data, but also the noise in the data. And that you want to prevent. And in order to do that, obviously you can reduce the number of parameters. And Dropout, in fact, just does that, right? Because it says, I'm just not going to allow you to use that many parameters, and zeroes out random parameters. So the network is forced then to allocate weights and to try to learn better through not memorization, but distribution of weight, which is what you want to do in order to be able to generalize better. So neural networks in general, they use regularization without thinking, because of the fact that invariably, as soon as you begin to grow the network any layers deep, you have such a large number of parameters that overfitting is the more likely, highly probable scenario. Whereas if you use any of the hands-on machine learning techniques that the HML book will teach, you don't necessarily jump to regularization there because it's not a given that there are too many parameters that you're learning. There, it's much more like SVM or other things, a mathematical thing, which don't have tremendous number of parameters to throw at the problem. But neural networks have this unique problem of just having the ability and having of learning very complex. I mean, they have the proofs that you can pretty much learn any function that's described, right? So, and they just have so many parameters in general, as soon as you go to any level of depth, that regularization is very common, because otherwise the networks tend to memorize stuff that they see in the incoming data.
Okay. Yeah. Thanks a lot. I think I got most of it. Yeah, but I should definitely do some reading.
Yeah, so I think of Dropout is very similar to, like, if you look at random forest, and the one of the pieces of random forest is the Bootstrap sampling, right? That's where you take you don't use all the samples in your training data for each tree. You just draw a sample with replacement from your data, right? So that each sample, each tree is going to exclude some of the data points, and that's very much like Dropout, right? Do you see what I'm saying?
Yep.
Yeah. So.
I mean, I understand overfitting really well, but the confusing part for me is that why can't you get overfit with smaller weights? Like, even if is it like impossible to get overfit if you have just smaller weights throughout?
It just limits. I think if you limit the size of the weights, that just limits what your model can do. And so if you let the weights have any values, then the model can be very general and can fit almost anything you throw at it. But if you limit the weights to be small, then they can't just fit the noise as well.
Okay. I kind of get it, but it's not fully intuitive.
Yeah. Well, have you seen examples where they show how you can fit you can construct a model that, if you give it enough parameters, you can fit a model that actually
fits every point. Yeah.
Right. It fits every point, but then in between the points, it has all kinds of wiggles and oscillations and goes crazy. And that's what they mean by fitting the noise. If you threw a new data set at it, it would do a terrible job, because its model is precisely constructed to fit every detail of the data of your training data.
Right.
Yeah, it's a good question in this sense that I haven't seen a mathematical proof, if you're saying, which would tell you that of how or why, and I'm sure it exists, because right, or why L2 regularization helps generalize better, but the intuitive explanations are the ones that Joseph and I are giving you. They may be I'm sure there is a mathematical explanation, and I think there is some level of mathematical explanation attempted to be provided in the ISLR book that I recall, especially in the chapter on regularization. So you may want to take a look at that, because I remember thinking that, at least in terms of, again, they don't provide a mathematical proof, but they tend to explain and give enough math basis for the reason as to why you would want to regularize.
I can just expand on my doubt a little bit more. I mean, probably it won't help, but like, weights are just what you multiply with the previous activation to get the next activation, and then from those activations, finally you arrive at a number, right? At your output layer, you arrive at a number, and then so if your weights are lower, what you get at the output would be a small number, and maybe a small number is what makes it overfit. So my point is, why can't you overfit with smaller weights? If that makes sense. So
Yeah, but
weight.
it isn't just that you. That's why I said it's complicated. The key point that you're raising is why can't you overfit with smaller weights? And it is, I guess, possible to possible to overfit with smaller weights. It just might make it less
Likely.
likely that it
Okay.
would overfit to any single parameter, which helps the generalization. You do agree that if you don't have any particular weight which is very large, you agree that that particular data point which that weight is related to would have
Yeah,
a
that
disproportionate
yeah,
impact on
I
the
got that.
output.
I got that part. Yeah, you don't want any one of them to be particularly big. That part I do understand, but yeah, I mean, this is what confuses me. The output layer is just a number, and you like, doesn't make sense that you would overfit only when that output is large. You can overfit even when that output is small, and the output happens, I mean, it becomes small when your weights are small. So ergo, you can overfit even when your weights are small. That is my question. If did that make sense?
Yeah, I think I understand what you're saying, but yeah, and I don't have a direct answer to that. I just think that um, I just keep coming back to when you allow the parameters to take on large values. Then, for example, for a cubic function, you can have more kinks and more extreme changes in direction.
But that's just
Right?
the number of like, if you give it x squared, x cube as your input variables,
Yes.
then you allow it to be more flexible. Does it have anything to do with the weights as such?
Yeah, the weights are the parameters. The weights are the A0, A1, A2.
It would be
For
just as flexible, right? I mean,
but if you limit
okay, okay,
the
if you're
parameters,
limiting, okay.
yeah, if you limit the parameters to take on small values, then the cubic that you fit, for example, is not able to have really big kinks and really large, really quick changes of direction. So that it's a weaker,
Yeah,
it has
but
less power to fit the noise.
but that brings back to my original question. Like, you can get overfit by having a smaller value, right?
I'm not sure that that's true. I'm not sure that smaller values allow you to overfit as well as larger values do.
Yeah, maybe it's.
I mean, it's extremely. I think what you're saying is, yeah, overfitting is overfitting, and I think that by limiting the sizes of the parameters, you're not completely eliminating overfitting. You're just making it harder.
Mm-hmm. Mm-hmm. Yeah. Yeah, I'll definitely do more reading on this.
I see your question, and I think it's a good question, and I can't answer it precisely. All I can say is that by limiting the sizes of the parameters, you're making it harder for the model to overfit.
Mm-hmm. Okay, I don't have any more questions.
Okay. Well, thank you so much for taking this last. This is really the hardest of all the pieces of this class. And if you don't mind, make the notebooks
Yeah,
that you created
yeah.
available.
I'll
Yeah,
just annotate it a bit more and post it on the Slack channel.
that's super.
Yeah. Yeah.
So
Thanks,
thank you so
Srinivas, and
much.
thank you.
Yeah.
Yeah. Thanks for answering my questions. Okay, if you don't have any more questions, we can end the meeting.
Okay.